Great to see you here again. My name is Luc de Ceuster. I'm founder of the Ceuster Academy, and this video is about Fermat's little theorem. But before starting with the video, please subscribe to our YouTube channel, click on the subscribe button, click on the bell button, and every time we have a new video, you will be informed about this. Pierre de Fermat was a French mathematician and lawyer who also contributed a lot to mathematics, also to discrete mathematics. There is also a very known theorem, Fermat's last theorem, that still has to be proven, but there are a lot of things that Fermat contributed. And one of the elements that Fermat contributed is Fermat's little theorem. And Fermat's little theorem is very interesting when we want to calculate, for example, 7 to the power 10 modulus. And I take 13. Now 7 to the 10th modulus 13, we can still do the calculations in a rather easy way. But when we have higher powers, these numbers become very quickly unmanageable by a computer, and we have to avoid this. Now what's very special about this is that the mode here is a prime number. And when we do the calculations here, we find that 7 to the 10th modulus 13 is equal to 4. Now there are different algorithms that we can use. We looked at the fast exponentiation, but when we have a modulus which is prime, we can use Fermat's little theorem. Now let's have a look at a different number, 135 to the power 9721 modulus 11. Now what is this? Well, we have to do some more complex calculations to find the solution. Now when we have the theorem, Fermat's little theorem, it states that when we have an integer to the power p minus 1, it is congruent with 1 modulus p. And p is prime. Now what does this mean? This means basically that p divides a to the power p minus 1 minus 1. We are not going to prove this theorem, we're just going to apply it. And in order to show that it's really working, we can try this on a very simple case. But let's take a case where we have a is equal to 3, so we have 3 to the power x modulus, and we take the prime number 5. Based on this, we can say that 3 to the power 4 is congruent with 1 modulus 5. And basically, we know this, and we have a basic statement. Now, you still remember, I hope, the laws that we have found or that we used when we work with exponents, with powers. And we know that x to the power a to the power b is x to the power ab, and x times a times x to the power a multiplied with x to the power b is x to the power a plus b. So these are things that we can resolve. Let us now say that x is 135 times 4 plus 3, and we find this is, in fact, we find the powers of 4. So what we find here is 3 to the power 4 to the power 135 is congruent with 1 modulus 5. Also, because we have the power 135 powers, and we still have here that 3 to the power 3 is in fact the last part that we have. So we can calculate the modulus here. So we keep on the remaining, we have the 3 to the power 4 times 135 has modulus 5 equal to 1, and we only have to look at this modulus 5. 3 to the power 3 is 27 modulus 5, which is equal to 2. So basically that's the application of the Fermat's little theorem on this exercise. But let's have a look at some other exercises. We have here some more complex solution that we can find, and I will look at a little different way how to approach this. Let us now try to find a solution for this before we go to the more complex exercise that I showed you before. Now what do we have here? P is equal to 11, is prime, so that's okay, and A is 2. Based on this, I can say, according to Fermat's little theorem, that 2 to the power 10 is congruent 1 modulus 11. Now what we're going to do now, so the first step we have here is 2 to the power 10. 2 to the power 10 is congruent with 1 modulus 11. Now we always double. We take the square of this, so 2 to the power 20 is congruent with 1 modulus 11. 2 to the power 40 is congruent with 1 modulus 11. 2 to the power 80 is congruent with 1 modulus 11, and 2 to the power 160 is congruent with 1 modulus 11. And we see the next one, 2 to the power 320, will be larger than 2 to the power 179. Now what we can say now is that 2 to the power 179 is equal to 2 times to the power 160 times 2 to the power 10 times 2 to the power 9. And we now know that 2 to the power 160 is congruent with 1 modulus 11, and the same for 2 to the power 10, that's the original one, is congruent with 1 modulus 11. So basically what remains is 2 to the power 9, and the only thing we have to do now is to calculate 2 to the power 9 modulus 11. We know that 2 to the power 9 is 512 modulus 11, and we can find, when we write 512 as a linear combination, or when we determine the parameter, let's say when we calculate the remainder, 512 is 46 times 11 plus 6. So basically that's what we find. So we can say that this gives us the solution 6. And our final conclusion in this case is that 2 to the power 179 modulus 11 is equal to 6. And that's the simple application of Fermat's little theorem. But we can do it a little bit different too. Let's have a look at that before we start with the more complex exercise. We have the result from the previous calculations. So we know that 2 to the power 179 modulus 11 with P is prime and 11 and A is 2. We can say that 2 to the power 10 is congruent with 1 modulus 11. Now what we can do is to look at 179 and see what it gives when we express it as powers of 10. So 179 is in fact 17 times 10 plus 9. And when we look at that, we find here that this is basically, we can say that 2 to the power 179 is equal to 2 to the power 170 times 2 to the power 9. And we know that this is in fact 2 to the power 160 times 2 to the power 10, and we know that this is congruent with, so 2 to the power 160 times 2 to the power 10 is congruent with 1 modulus 11. So basically what we know from this is when we express this as a function of p minus 1, excuse me, we find in fact that we can reduce this expression as 2 to the power 9 modulus 11, which gives me in the same calculation 512 modulus 11, which is again, of course, equal to 6. So that's a different way to do it. It's a little bit faster, but it's basically using the same calculations like we did before, but we can go through the exercise a little bit faster. Let's now go to the more complex exercise, the value. We try to find the expression or the result of the number we saw at the beginning of this video. Remember the number I gave you at the beginning of this video? It was the 9721st power of 135 modulus 11. So basically what we have here when we write the theorem of the little theorem of Fermat, we can say that this 135 to the power 10 is congruent with 1 modulus 11. Now we can do all the calculations, all the steps, 135 to the power 20 and so on. But we can immediately go faster. We can say that 9721 is 972 times 10 plus 1. And we know that this part from the Fermat theorem, we know that 135 to the power 972 times 10 is congruent with 1 modulus 11. So basically the remaining thing that we have to do is to calculate 135 to the power 1 modulus 11. And now it becomes very easy because we just have to write 135 as a function of 11 is 13 times 11, which is 132, plus 3. So basically the solution of this problem is that 135 to the power of 9721 modulus 11 is equal to 3. So basically when we see that we have a modulus, when the modulus is a prime number, we can find the value, the power of the value that we have modulus p very quickly, and we don't have to use the exponentiation algorithm. This is very interesting to do calculations a lot faster, and it's very interesting since we're going to use prime numbers. So Fermat's little theorem is very useful when we're going to look into those modular exponentiations, modular a prime number. That was the end of this video. Don't forget to have a look below in the description. You find links to our website, theceusteracademy.com. You find links to the different courses that we offer, and with every course we have a very interesting coupon that will give you a great discount. Anyway, before stopping, before quitting, do not forget to click the subscribe button if you didn't do it yet. Click the bell button so every time we have a new video, YouTube will let you know. Thank you very much and bye-bye.